a hierarchical fork-based architecture for IoT-enabled intelligent traffic light system services. And unfortunately, I will have to repeat some things Athanasios said before about fog computing. The term was initially introduced by the Cisco Systems in January of 2014 as a new model to ease the wireless data transfer to distributed devices in the IoT network paradigm. Fog computing is a paradigm that extends cloud computing and service to the edge of the network. It places processes and resources at the edge of the cloud and often on network devices, while data remains mostly stored in the cloud. Thus, this leads to faster processing times and fewer resources consumed. So why fog computing for ITS systems? Because it demands it. As reference for states, ITS applications have intrinsic characteristics regarding the way they process, store, and disseminate vast amount of data generated. So designing ITS applications that have required quality of service is a challenge. The benefits for designing ITS with the fog paradigm are described here: low latency, predominant wireless access, wide geographical distribution, real-time interaction, mobility, scalability, and accessibility. Some related works at reference 5, Luis Cruz Piris et al. They propose the use of a multi-agent system composed of 3 types of agents: traffic light management agents, traffic jam detection agents, and agents that control the traffic lights at an intersection. At reference 6, visit Hirankiti et al. They propose another multi-agent approach that consists of car agents, road networks, traffic lights, etc. And each of these agents control all traffic lights at one road junction by an observed think-act cycle. At 7th reference, Luis Cruz et al. Again, 1 year later after the previous proposal, they extended their work to use the centrality measurement of a graph as a base to find the best locations for sensors in traffic network. And finally, at 12th reference, you can find by Zadalos Fotios et al. Extensive review of related works. So the proposed ITS and ITLS architecture. Actually, there is in the literature the difference between ITS and ITLS, which stands for the second, for intelligent traffic light systems, and the first for intelligent transportation systems. It's not really clear. Also, the first sounds more general, but it's not really clear. The second, it's more specific regarding the way they manage the traffic lights, as the name states. So what we propose is a hierarchical multi-agent architecture which exploits the fog computing paradigm and the Attica framework to provide the necessary structures and semantics for the implementation of urban demand responsive ITS services. The architecture consists of a distributed network of actors that form a hierarchical tree structure and act as traffic controllers in an urban geographical zone. The optimization goals are a reduction of delays for emergency vehicles, which for obvious reasons, minimizing total vehicle delays on the network, which will contribute in decreasing carbon dioxide emissions. Eliminate total pedestrian delays at the intersections. Most of the urban traffic control systems do not take pedestrian traffic into account, which is considered as an unfair treatment. And finally, accident prevention by issuing slowdown warning to vehicles and pedestrians. So, agents as actors. Akka uses the actor model, which provides a level of abstraction and facilitates the development of distributed and parallel systems. In that context, our architecture consists of actors that act as traffic controllers in an urban zone. And we'll see a brief explanation about the corresponding role and certain function of each component of that architecture. So, zone controller actor, the root agent of an area zone that is responsible for managing the entire network, defines the, sorry about that here. What I mean is the defines and disseminates traffic control policy, monitoring the network of intersection managers, receipt and recording of reports to analyze traffic flow models, and disseminate the changes in the topology of the road network. Intersection manager actor receives traffic policies from zone controller actors and traffic model information from adjacent intersection manager actors, monitoring of data, selecting an appropriate traffic policy according to the current context, exchange of traffic state information with zone manager, sorry, again, wrong here, zone controller actor, supposed to be. Flow actor receives information from traffic detector. Traffic detectors are sensors that generate real-time data, such as video cameras, induction loop, contracts the traffic flow profile, and there are two traffic flow profiles. The vehicle flow profile, which is at an intersection according to the information it receives from the traffic no, sorry. Sorry for the inconvenience. It constructs these two traffic flow profiles, and the vehicle flow profile, it's actually an queue which contains information about the time a car entered at an intersection, its speed, and the similar information shares the pedestrian flow profile. So, intersection manager actor, critical role for enforcing security, vitality, and impartiality aspects of the system, monitoring traffic light actors passively and actively, makes control decisions, transmits them to traffic light actors, and in order to do that, to achieve that, in order to achieve a secure, optimized traffic flow, the zone controller actor have to profile traffic information for neighboring intersections and zones. And finally, the traffic light actor is directly connected to the traffic light actuator responsible for either displaying or transmitting decision to vehicles and pedestrians, sending its state information and other context-related data. And finally, the event persisting actor is responsible for storing generated data, operates in a synchronous way, and it's an extremely useful tool for generating analytics. Implementation issues. So in our pilot implementation, lightweight virtualization applied through Docker containers. It's known that this techniques allows us to decouple hardware from software. It also fits properly into the requirements for creating efficient edge services. Future work. This approach has led to applying clustering, which is facilitated by this framework and can be useful for eliminating the single point of failure. Another future extended work could be deploying on a resource management and orchestration platform such as Kubernetes, and extending system features to include smart street lights and road anomalies detection, as described by Zandalis Fotios et al. So, to conclude, the fog computing paradigm and the Attica framework capabilities give the potential to build a truly distributed hierarchical architecture as well as an anerously efficient implementation, as the first result of our pilot application show. The completion of the evaluation of our approach through extended simulation as well as further addressing and optimizing the decision modules of the system are a high priority in our future work. These are the references, and thank you for watching, and if there are any questions, I would like to hear.
Okay. Leodios, thank you very much for your presentation. I suppose there is no echo now. Okay. Thank you very much for your presentation. And we have one question for the beginning for Mr. Piraeus. You can make your question. Do you hear, Mr. Piraeus?
Hello.
We cannot hear you well.
Can you hear me?
Yes, now. Okay.
Can you hear me?
Yes, we can hear you now.
Yes, we can hear you now.
Okay.
Go on.
So I did. Okay, I didn't quite understand the protocol used between the vehicles and the traffic lights. Sorry, it was moving a bit fast. The presentation was moving a bit fast. So my question was what protocols you used for communicating between the system and the vehicles or the traffic lights, and if you have do you have a demo of the project, or is it just on a research material that you cannot share?
Okay, can I answer?
Yes, Leodios. Yes.
Okay, well, this is a pilot implementation, and regarding the way that traffic lights communicate with vehicles, it was a vehicle-to-infrastructure communication, which is beyond our implementation purposes. It's not implemented in this scope. Yes, there is an implementation with some results, and but it lacks, if I may say, some truly world scenario results, because our initial scope was to propose the architecture, and it's an ongoing work.